So, yep. I know we need the. Okay. We're starting. So, for our next talk, we are happy to have Argam Ohanyan speaking from University of Vienna, and he'll tell us about the splitting theorem for globally hyperbolic Lorentzian link spaces with non-negative time-like curvature. Go ahead. Thank you.
Thank you so much, Eric. So I want to start by thanking the organizers for this very nice and interesting workshop and for the opportunity to speak here. So I will report on a recent result, namely the splitting theorem for globally hyperbolic Lorentzian length spaces for non-negatively time-like curved spaces. This is recent joint work with Tobias Beran and Felix Roth from the University of Vienna and Didier Solis from the University of Yucatan. So this is how the talk will be structured. We'll say a few words about splitting theorems in general. Then we'll go over some basics on Lorentzian length spaces, but not stay too long there because this has been said many times already in this workshop. We will talk about angles as Tobias presented them on Monday. We'll talk about product spaces in the synthetic setting. Then we'll present the main result that we have obtained. And then the rest of the talk will be dedicated to highlighting the main ideas and main constructions that go into the proof. At the end, we'll apply this to several classes of spaces where, let's say, most of these assumptions are very natural, in particular, low regularity spacetimes. And then at the end, give an outlook as to what future problems one can have a look at in this context. Okay, so what are splitting theorems? So first of all, splitting theorems appear in various branches of geometry, right? Riemannian, Lorentzian, Alexandrov, metric measure spaces, and so on. And it's usually kind of a sign of a good and stable geometry that there is a splitting theorem in there. And they all essentially have this form. So X is some complete space, where complete is, of course, depends on the geometry. Non-negatively curved, and it has a global complete distance realizing curve gamma. Then X splits as R times Y, and the factor R in this product space is represented by the curve gamma. So this is essentially how all of these theorems look. And the idea is that non-negative curvature kind of promotes the formation of conjugate points along geodesics, and after conjugate points, of course, geodesics stop maximizing, distance realizing in general. And the fact that we assume the existence of a global distance realizer is kind of an anomaly, and splitting theorems tell you that this is only possible in special cases, meaning in product spaces. And in the context of Lorentzian geometry, this was a huge undertaking in the 90s and has been established in various papers by very renowned authors. So maybe let me highlight the very first paper here by Beam, Ehrlich, Mark Borston, Galloway, which proves the Lorentzian splitting theorem under the assumption of non-positive time-like sectional curvature, which will be, let's say, the main source of Lorentzian inspiration for our result. Okay, so what are Lorentzian length spaces?
Your conclusion is that geometrical splitting, right?
Yes. So Lorentzian length spaces were introduced by Kunzinger and Seemann as a synthetic analog of Lorentzian manifolds, let's say, or a synthetic setting for Lorentzian geometry. We've heard a lot about these spaces already, so let's go over them rather quickly. So Lorentzian pre-length space is a quintuple xd less equal and tau, where x is a set D is a metric, less is the time-like relation, less equal is the causal relation, and tau is the time separation function or Lorentzian distance function. And one can define lengths of causal curves as infima over such partitions of the interval and such sums of time separations along the curve. There is the notion of localizability, which is kind of the synthetic analog of normal or convex neighborhoods. Let me maybe, so I don't want to dive too deep into the details of that. Let me just mention that there is the notion of regular localizability, and the most important thing that, or the most important property that regularly localizable spaces have is that maximizers in such spaces have causal character. So this will be extremely important in the context of the splitting, because then we can say that whether some, from some maximizer not being null, we can conclude it's time-like and so on. So this is very essential to have. Lorentzian length spaces are pre-length spaces with some additional assumptions, and the most important one being that the time separation is obtained as a supremum over future directed over lengths of future directed causal curves between the 2 points. And so a very nice result is that the Aves-Seifert theorem from Lorentzian geometry still continues to hold for globally hyperbolic Lorentzian length spaces. So points have maximizers between them, and the time separation is finite valued and continuous. There is the notion of geodesics in such spaces. For all intents and purposes, we can understand them to be locally maximizing curves. So curvature bounds can be studied in the synthetic setting via time-like triangle comparison with model spaces. And some will need some results on extensions of Lorentzian length spaces, as discussed by Grant, Kunzinger, and Seemann. So an extension of a Lorentzian pre-length space is essentially a nice embedding, preserving all of this causal information. We will talk about this later anyway. Okay, so angles. So this was talked about in detail by Tobias on Monday. So they were introduced by Beran Seemann and by Barrera de Oca and Solis. And so they essentially kind of, let's say, take the approach from Alexandrov geometry. So how does this go? If you have two time-like curves starting at the same point, then you define the angle or hyperbolic angle between the two curves as the lim sup over comparison angles in some comparison space. Yeah, and such angles have signs where if both curves are future or past, then you say the sign of this curve is negative or -1, and positive if one is future and one is past. And then you define the signed angle as the product. And what is the most important property, or the most important ingredient about angles that we'll need, is that one can characterize curvature bounds with angles. So under some connectedness assumptions on X, it is true that X has non-negative time-like curvature or non-positive time-like curvature if and only if one has some monotonicity properties on the signed angle, on the signed comparison angles. Okay, so let's talk about products in this setting. So, very generally, warp products I times with a warping function f x. These were treated in this paper by Alexander, Graf, Kunzinger, and Seemann. But it was kind of not really advantageous for us to require curves from the get-go, so we kind of build it from very basic building blocks. So we take some metric space xd, define the product r times x, take a capital D to be the product metric, define the causal and time-like relations as such, and for causally related points, we define the time separation via the, let's say, essentially the Pythagoras theorem, and otherwise we define it to be 0. And such spaces are very nice, as one can expect, right? So the time separation is obviously continuous. These spaces are globally causally closed, strongly causal, non-totally imprisoning, and global hyperbolicity is equivalent to the metric properness of xd. Yeah? And maximizing curves in R times X are in a one-to-one correspondence with minimizing curves in the metric space X. Yes. So this is something that, especially in the context of limit curves, this will be very important to have that the background metric is proper. But yeah, this is, for example, something that in the context of spacetimes, even low regularity is a non-question because you always have a background complete Riemannian metric. So this is for sure always satisfied. Yeah, so this is the main result. So let X be a connected, globally hyperbolic, regular, so regular meaning regularly localizable Lorentzian length space with proper metric D, and global time-like curvature bounded below by 0. Global meaning that I have triangle comparison for triangles of arbitrary size. Satisfying time-like geodesic prolongation. What does this mean? This means that, so essentially the form that we will need is that maximizing time-like segments always extend to locally maximizing curves on an open domain. Again, this is something that, due to the geodesic equation in spacetimes, this is a non-issue, at least in sufficiently regular spacetimes. And of course, we assume that we have a complete time-like line. Complete meaning that the two subrays defined by gamma have infinite Lorentzian arc length. Then we've shown that there exists a time separation and causal relation preserving homeomorphism from the product space into R times S into X. Of course, the inverse is then also time separation and causal relation preserving. And S is a proper, strictly intrinsic, meaning geodesic metric length space. Yeah? And as a corollary to this, we get a nice characterization or nice foliation of X by Cauchy sets. So if X is a splitting space as above, then all of these slices T times S sit inside X as pairwise homeomorphic Cauchy sets, and the projection to the time essentially is a Cauchy time function on X, where these notions were introduced by Bucha and Garcia-Heveling in their 21 paper. Okay. So how do we prove this? So the approach is that we kind of know how to prove a Lorentzian splitting by a triangle comparison due to this 85 paper by Beam, Ehrlich, Mark Vorse, and Galloway. And we mix this with, let's say, synthetic methods that were very successfully used in a proof of the Alexandrov splitting, as can be, for example, read in this classical textbook by Burago, and Ivanov. So how does this go? So we have gamma. We take points in I of gamma, where I of gamma is the future intersected with the past. And we construct co-rays to gamma by connecting going from P to points on gamma and then sending these parameters to infinity, right? This usual construction. We use our triangle bound to show that the time-like co-ray condition holds, that any such ray we get as a limit is time-like, and that all of these have infinite Lorentzian arc length. Yeah, and we then show that any such, so let me call them asymptotes from now on, any such asymptotes, one to the future and one to the past, fit together at their common point to give a time-like line. Yeah, so essentially what one gets from this is a, let's say, a foliation of this I of gamma set with time-like lines, all of which were constructed via asymptotes to gamma. Yes. Yeah, that's a very good idea.
I'm already lost.
Sorry. Yeah, so I of gamma is I plus of gamma intersected with I minus of gamma. So these are all points that I can relate to gamma in a time-like way in both directions. So if this is gamma, and let's say this is P, then I construct these asymptotes by going here, where this is, let's say, gamma of Rn.
Oh, okay. So gamma is the doubly infinite one, right?
Yes.
So that's so by going to plus or minus infinity, that's what's allowing you to.
Exactly. So I continue doing this, and then I get a ray here, and via the curvature bound, we can show that this is a line. Yeah. But so now in this synthetic setting, we somehow need to get a control on what these what these lines that we get as limits do, because in the smooth setting, you know what these lines are. These are geodesic flow lines of the gradient of the Busemann function, so you understand them very well. But here, this is a kind of a priori, it's difficult to know what they do. So we introduced in the spirit of the splitting theorem by Alexandrov, we introduced the notion of parallelity for time-like lines via isometry to lines in Minkowski space. And then we show that all of these asymptotes, they are all parallel. And then we fix a parametrization, which fixes a cross-section across all of these lines, which is essentially the zero locus of the Busemann function. And this then establishes the local splitting, because I can just go on this cross-section and up on any asymptote, and this is then the splitting. And then we show that this I of gamma has the time-like completeness property, and then by a result due to Grant, Kunzinger, and Zeeman, we get that I of gamma cannot be extended as a regular Lorentzian length space, but since X is regular, we get that I of gamma is all of X. Okay, let's maybe dive a little bit more into details. So the first thing that we'll need is this stacking principle of comparison triangles, which means that under our curvature bound, if I draw triangles that have a common side and they kind of lie, so basically triangles of this form, which have one side adjacent to gamma and they lie on top of each other, then I can, of course, construct the corresponding comparison triangles in Minkowski space. And then what the stacking principle says is that I have no break on where I put them on top of each other. So this is very heavily uses that gamma is a line, as well as the curvature bound. So this is an analog of a result given by Burago, Ivanov in their Alexandrov proof. Okay, so I've already said how these asymptotes are constructed via the limit curve theorem. So we show that they are time-like and that they have infinite length. And again, due to the stacking principle of comparison triangles, these triangles that I draw here, they translate one-to-one to the corresponding comparison situation in Minkowski space. So it's very easy to see then that what I get in the limit is a line and not just two rays that fit at the point. So yeah. So now comes this notion of parallelity that I mentioned. So if alpha, beta are complete time-like lines, we call them parallel if we can map them in a time separation and causal relation preserving way into Minkowski space, such that they are time-like lines in Minkowski space affinely parallel. Okay, and then of course after composing with a transformation of Minkowski space, I can have them vertical. And once they are vertical, they have a uniquely defined normal distance because Minkowski space is Minkowski space, right? So I have a natural distance between such parallel lines. And again, due to the stacking principle, one can show that this construction yields that any asymptotic line that I construct to gamma is parallel to gamma. And then as a consequence, one then shows that they are all in fact parallel to each other. Okay, so what do I do now? So I fix a Lorentzian arc length parametrization of gamma by fixing gamma of 0. So I start parametrizing at gamma of 0, and then I fix a tau arc length parametrization for these asymptotic lines such that they are synced to gamma, where synced means that I have let's say a parallelity realizing map F mapping gamma to t, 0 and the other asymptote to t, c, where c is their normal distance. Okay, then I call S the set of all alpha of 0 where alpha has been synced. So alpha is a synced asymptote. I call this my space-like slice, and this is nothing but the zero locus of the Busemann function of gamma. And on this S, I can of course define the distance between 2 points as the normal distance of their corresponding asymptotes. Then I have a very natural splitting map going from R times S into I of gamma, taking t, p to the asymptote alpha that gives p at 0, and then I flow up to time t on this asymptote. And then these maps are very easily seen to map time-like and causal diamonds to time-like and causal diamonds. Hence, they are homeomorphisms because both sides are strongly causal. Okay, and one directly shows that the product space is globally hyperbolic, but this is equivalent to the metric properness of S, and S is also geodesic because I can map a maximizer in X or in I of gamma to R times S and then project it down to a minimizer in S. Okay, so now this establishes the splitting of I of gamma, so I need to globalize it. So what do? I use this result by Grant, Kunzinger, and Simon that I mentioned, that strongly causal Lorentzian length spaces where each inextendable time-like geodesic has infinite arc length cannot be regularly extended, and apply this to I of gamma. And how do I do this? Well, if I have any inextendable geodesic on I of gamma, map it to the product, project it down to S in S, I can certainly extend because it is proper, projected back into I of gamma, and I see that I of gamma, in I of gamma I have an extension, and so this shows that. Yeah, so I don't have too much time, unfortunately, so let me go over this quickly. So in the smooth setting, we get a weaker result than the one proven by Beam, Ehrlich, Markworth, and Galloway, but via some additional work, one can kind of see our result or use our result to get a final detour in the proof of the smooth splitting result. In the C11 case, there is no more sectional curvature, so we have to assume triangle curvature bounds, and then we get a corresponding synthetic splitting. In the case of C1 spacetimes, one needs to assume this prolongation property because this is no longer satisfied for C1 metrics, and then one still gets the corresponding synthetic splitting. And to give an outlook, so in the future, I think we should have some more detailed look at what these low regularity splittings look like, because they will certainly be better than just synthetic. So they will have some higher regularity. And so in the spirit of Yao, maybe it will be interesting to look at whether the splitting is possible not for globally hyperbolic spaces, but for TC spaces. And so recently, time-like Ricci curvature bounds were introduced to the synthetic setting by Cavaletti Mondino, recently extended by Brown. And so one knows that in the positive definite setting, the CD condition is not sufficient for a splitting result, right? The RC and the RCD splitting result was proven by Schily. So we need a kind of Lorentzian TCD condition and a kind of space-like hypersurface or submanifold theory to continue working in this direction, but this technology is currently unavailable. But this is definitely something that will be very interesting to look at in the future. Okay, thank you very much.